say it's up to time. Okay, welcome back everyone to the second part of this morning session. Our next speaker is Matthias Ehrhardt from the Department of Mathematical Sciences at the University of Bath. There he is a Leverhulme Early Career Fellow. Matthias got his PhD in 2015 from UCL. And then after postdoc first at UCL and then in Cambridge, he moved to the University of Bath, where he's also Prize Fellow at the Institute for Mathematical Innovation and co-director of the Center for Mathematics and Algorithms for Data. So today, Matthias will talk about the equivariant neural networks for inverse problem solving.
Thank you so much, Tatiana, for the very kind introduction and for the audience for the invitation. It's such a great pleasure to be back in person. So this is my first in-person talk since 1.5 years or so. So it kind of like feels weird, but also like it's a very positive weirdness that one is experiencing here. So kind of like the talk in a nutshell. So yes, indeed, I will talk about equivariant neural networks for inverse problems. But kind of like what this is all about is about to bring mathematical guarantees into like if you want to solve inverse problems via deep learning. And this is this joint work with like a number of people. To highlight maybe like one person here, that's Ferdi Sherry, a joint PhD student of mine, and Carola, who just submitted his thesis, who did the majority of the work here. All right, the outline of my talk goes as follows. So first of all, I would like to give some small introduction into inverse problems and how this potentially connects to machine learning. Then we talk about equivariance, and then finally I would like to conclude the talk with some numerical results. And although I now wrote this as 3 parts, actually like the part 2 is by far the biggest. So I could have equally like, split up this part in like 3 parts, and then we would have like 5 equal parts. All right, and like in case you want to know more about what I'm talking about today, stuff like our paper just got published in inverse problems. All right, so inverse problems and machine learning. So you all know what inverse problems are, but maybe like to kind of set the scene, to kind of like set the notation. So we want to consider inverse problems where we denote the for operator with A that maps some sort of desired solution U to our data B, and then obviously like the goal is to recover U given B, given data B. And so we are interested in 2 inverse problems here, or like in the application section later on we will consider 2 inverse problems. So the first one is CT, where the for operator is the X-ray transform. And the second one is MRI, where the for operator is a subsample Fourier transform. All right. And I mean, as you all know, there are various ways how to solve inverse problems. One very dominant way over the last couple of decades is so-called variational regularization, where we try to sort of like approximate our original solution U star with a solution U hat that is a minimizer of such a cost functional, where the D is data fidelity, which kind of measures how close we fit measured data, and R is a regularizer that sort of like says like how regular is the solution, and then lambda is a regularization parameter which trades off those 2. And so like a lot of work has been into sort of like designing good regularization functionals, and then sort of people came up with a total variation or total generalized variation. And so here's one example for image denoising. And actually, so like these kind of regularizers, they work really, really well if you have something like a geometric phantom, which is fairly simple, but then they're not that great if you have like more realistic images, which maybe like a lot of like fine details and so on. But then so like how to actually solve image problems. I mean, like this like variation regulation framework, it's more like a mathematical framework. You still need an algorithm to compute such minimizers. And then, so like as you've seen, like in the previous talks, of like she outlined various ways, like gradient descent, ADMM, and so on, how to solve it. Maybe let's look at one of these methods in a bit more detail, which is proximal gradient descent or for backward splitting. And the algorithm goes as follows. So like first we do like a gradient descent step on our data fidelity, and then we do a proximal step on our regularizer, where the proximal is defined as this. And having this algorithm, we can then define a mapping phi that maps our data B to the limit of this algorithm. Assuming obviously kind of like this limit exists, but so like under like fairly mild assumptions on D and R and on step size, we can prove that such a limit exists. It's unique. So like this makes sense. And so then, sort of like in practice, it works like you need to choose certain step sizes, you need to choose a regularization parameter. And then we have our mapping that maps for like B to our model solution U hat. And then we can prove that, for instance, I mean, as the noise level goes to 0, as the regulation parameter goes to 0 in a certain way, then we actually converge to our desired sort of like noiseless solution of our inverse problem. And then one option, also I mean, same as we have seen like in the previous talk, how you then can insert machine learning into such an algorithm is by taking this algorithm and essentially replacing this prox with a neural network. So here we do like even like one step further, where sort of like so even this like gradient descent type of step, here like we replace also like the neural network has two inputs. So our previous iterate UK and the gradient, and then like it spits out a new iterate. And then our solution mapping just like maps the data to UK, where we iterate this like a couple of times. And now one big computational benefit is now here this capital K is usually small, like 5 or 10. In contrast to the original algorithm, where we really are interested in the limits, we really want to have a lot of iterations such that this approximates well the model solution. And so then, like in practice, we want to learn parameters for these neural networks, such that the solution mapping now shouldn't be close to any model solution, but should be close to our ideal solution, like independent of the noise level. You always want to be as close as possible to the ideal solution. And so like this is how it looks like in practice. So like this is now like a bit more complicated version compared to what I've shown you on the previous slide. So here there's some memory S. So therefore sort of like we have, and also here I changed notation a bit. So like what used to be X before, so like now is U. So we have basically like two variables which is kind of like our current version of the image, now called U, and some memory S. Then we compute the gradient, put this all into a neural network, and this spits out the next iterate and the next memory. And then we can iterate this like a couple of times, and then we get our desired solution. Okay, so now on to equivariance. So first of all, so like kind of what is equivariance and why are we interested in this? And so like assuming, for instance, we are in the case of denoising, and then we have our data B. So what if we now observe not the noisy image B, but a rotated version of it? So then like it kind of like it's intuitive that ideally you have that the output, when you know like apply some denoiser to it, is then nothing else than the rotated version of the denoised B, right? So that kind of feels quite desirable, that is robust in terms of rotations. And so kind of this property you call that something is equivariant with respect to rotations. So here's some examples. Here we have some noisy image on the left. And so here we train a standard convolutional filter, and here we train something that will tell you like a second what it is. And so like both of these methods, they're able to kind of denoise these image of stripes very well. But like what happens when we now rotate the image of stripes? So during training time, they were always only horizontal stripes, but now during test time, we now look at vertical stripes. And now the standard convolutional neural network then kills all of this, and you can see that like the noise is being spread out in a horizontal direction, right? So like it learns that it needs to denoise in a horizontal direction, so like it kills all the structure. Whereas now here the new method that we'll talk about in a second, so like doesn't do that, but like performs equally well, even though the image is being rotated. Okay. So but now how do we get such equivariant mappings? And so, kind of like in the literature, what is usually being done is an approach that is fairly heuristic, and it's called data augmentation. So if we have pairs of data, BI, UI, and like those denoise, you can think of like BIs as noisy images and UI as the clean versions. Then we augment the data to become sort of like we rotate the noisy images and the denoise version. So our data set becomes much larger, and so we now have like all the possible rotations, whatever this now means, in there, and then we train on this new bigger data set. So this is very simple to implement, right? So like instead of choosing data points from the original set, we just like choose data points from the new augmented set. So that's like any algorithm or any training algorithm that you've implemented before that works on this one very easily works on the augmented one. So that's great. It's potentially computationally costly, right? Since the data set now became a lot bigger. There are no mathematical guarantees that this will translate to new data, right? So like because I mean, for example, in terms of like rotations, right? You have like an infinite number of rotations you potentially could have, and so like you probably like would want to like sample like a finite number, and so like what happens with the rotations which are not in the training data set. But also, I mean, there's no guarantee that what you train actually will be equivariant, even with respect to the rotations which are in the training set. And then another problem with this approach that it's not always easy or possible to implement this for arbitrary inverse problems. So like in terms of image denoising, it's actually like quite easy to do. But if you are in arbitrary inverse problem settings, so like what exactly does all of this mean, right? So because you can't rotate the data, right? So like if you think about the BI as case-based measurements in MRI, so like what does it even mean to rotate that? So if the BI are simulated from some ground truth sort of images UI, then you can always do it, right? You can rotate the ground truth thing, then simulate what the BI would be. And so like in a simulation setup, you can do it. But if your train data comes from a real scanner, then this is like by no means clear whether this is possible or feasible, right? So in this talk, we would like to do a different strategy, and we want to do equivariance by design. So we want to design neural networks which are provably equivariant, like no matter what the training data is, no matter how you choose the parameters and so on, but you're always equivariant. So it's like mathematical guarantee that you are equivariant. But then as a downside, this is obviously like not trivial to do so, and that's the reason why I'm talking about this today. Equivariant neural networks have been studied a lot in the literature for image-based tasks like segmentation, classification, denoising. And so here at the bottom, you can see like a few papers which appeared over the last couple of years, but there are many, many, many more. So like in image-based tasks, like in computer vision, so this is a very, very popular approach, but sort of like so far hasn't been translated to inverse problems. And so maybe like from all the literature to highlight perhaps one paper, see the one by Weiler and Chesa, where a couple of the ideas and algorithms that we use later on are based on. Okay, so how does now equivariance and inverse problems fit together? Because I said before, sort of like, I mean, you can't rotate your training data usually, right? So what exactly should be equivariant? And so now if we call so like A our for operator and then phi our solution operator mapping from Y to X. So now, for instance, to ask that phi is equivariant doesn't really make too much sense, right? So because I mean, like the X usually like are images, so it like makes sense to talk about rotations, but then the Y is the data, so like it's not really clear, sort of like what action you would want to have on Y. So this is equivariant. Okay, so like where like in general like this doesn't make sense to ask phi to be equivariant, but what we could hope to have is that phi composed with A, right? So this is a mapping going from X to X, going from image to image. So this might be equivariant. And so like in terms of like rotations, which means it's sort of like if you now apply your rotation to an image, then you apply A, then you apply the reconstruction. This should be the same as you first apply A, then reconstruction, and then the rotation. Okay, so here's now sort of like some picture of what this could look like, right? So here's right now some image of a pig here on the left. And so for these two things to be the same, kind of these two paths need to be equal, right? So like we have the image of a pig. We now rotate the image. Now here this is in painting. So we now like have a mask. So we like don't observe this black square here. So a for operator selects everything but what is like hidden behind the black mask. And then our reconstruction here is a variation into a variation in painting, which sort of like does a fairly fine job, right? But also like there's like no texture like on the mask. On the other hand, if we first sort of like observe a number of pixels, then we do the in painting and then we rotate, we can see obviously kind of like that the mask which we have observed, right, is different in these two things. And if the in painting isn't perfect, right, then these two solution paths would be different. So, like phi composed with A is not rotationally equivariant for variational TV in painting. And the reason is that sort of like something is not being observed here, right? And so like as long as your reconstruction isn't perfect, you might not be able to have that these two things are the same. But now, what about if we have a kernel? Because like the problem here, right, is that we have a non-trivial kernel. And so like one question is, so like what about like inverse problems where we don't have such a kernel, or where we have a reconstruction operator that sort of like finds the right elements from the kernel, for instance, such as like incorporate sensing. So perhaps there we might have a property that phi composed with A is indeed equivariant. But that's kind of future work. Okay, so like in this direction also then we can prove a small statement. So like in general, variational regularization is not equivariant. But what we can prove, like if X is like some sort of like function space that represents images, for instance L2, and then our regularizer, now called here J, is invariant with respect to rotations, which mean that like if you have an image and you rotate it, then you have the same functional value. That is, for instance, the case as in total variation, total generalized variation, and so on. Then it turns out that the prox operator is indeed equivariant. So when you apply the prox to the rotated version of the image, that's the same as you rotate the prox of the image. And so therefore, sort of like in a learned gradient descent framework where we have replaced basically the prox operator with a neural network, now it's a very natural condition that maybe like as the prox was equivariant for like many of the models that we're interested in, so perhaps also like the network that we replace the prox with should be equivariant. Okay, so now equivariance revisited. So like everything I said before was about the special case of rotations. Now we want to make this a bit more abstract. So now we need to have a couple of definitions to be on the same page. So what is general equivariance? So equivariance is usually being defined with respect to a group. And so like for all those of you who have never have taken Algebra 101 or like it's a long time ago, so a group is defined in the following way. So like it's a set, right? So the G is a set. And where we have three axioms. So like on the one hand, and we have like an operation that acts between the group elements. And so like we need to have that the group action is follows associativity axiom, where so like it doesn't matter in which order we apply the group actions. Then also we need to have like an identity element such that when you apply the identity element to like another element, then you get the element back. And also sort of like every action needs to be invertible. So but now sort of like the images that we're interested in, so like they themselves like don't form a group. So we now need to relate sort of like for example rotations to images. And so now we can define how a group acts on a set X. And so now we have sort of like another action, sort of like how this works, which now to take a group element and an image X and gives you your image X as an output. So this needs to be defined, and this group action now sort of like also sort of like needs to have that if you apply the identity to an image X, then you get the image X out, and it needs to be compatible. So like how G acts on X needs to be compatible with the original group action. So so by the way, so one word of caution. So now I use the same symbol here on this dot and that dot, right? No, this dot and that dot. These are two different dots here, right? So this dot here is how a group acts on an image. Whereas this dot is how two group elements act on each other, right? And so kind of like so it's like how group acts on images needs to be compatible to the group action, right? So like in this way. Okay, so now as we like define what groups are and how groups act on images or any arbitrary sets, so like we can now like define what does it mean to be equivariant. So if we now have a group which acts on two spaces X and Y. And the group can act differently, so like on X and Y, or can act the same, if it makes sense. Then we define, we say like a mapping phi between X and Y is called equivariant, right? So like if the group action, so like as a group element acts on X is the same, and then we apply phi to it is the same as the group element acting on phi of X, right? So that's what we call equivariant, and it's called invariant basically. So like if this action here is trivial. So if there's no G here on the left-hand side, then we call it invariant. Okay, so this was now like fairly abstract. So like how does it work in practice with images? So there are now various ways how groups, like rotations, for instance, and so on, can act on images. And so on the one hand, it can act on its domain. So group acting on an image is defined as that the inverse of the group element, so acting on the input of the image. Right, so like this, we can, for instance, then like define rotations and scalings and so on of images. But then so like there are like other ways. So here are a few examples, but I don't want to go into too much detail here. But then the group can also act on the range, right? So like that, the group acting on the image is defined as now the group acting on this element here. So like, did I now give this a name? I don't know, like this before, like in Y, right? So that you evaluate first at X and the group acting on this one. Okay, but also, and this is something that we will use in the following, the group can act on both the domain and the range, for instance, kind of like in this way, basically like composing these two things together. Okay, so, and I mean, there are many groups, and so but here we are interested in a particular group, and this group we call a G bar. And so this this group is composed of, let's say, like two subgroups, or like two groups itself. And so like one of them is a subgroup of the general linear group. So you can think of H as like rotations, for instance, and then the Rn comes in for translations. So now sort of like we have that the G acting on X is we rotate the X by some rotation matrix from H, and then we apply some additive shift to it, so we translate this one. And so now sort of like having such a group, we can now sort of like have that the G acts on an image U, which is a function, right? And such as that we take the inverse of the element acting on X, right? So this is how the inverse looks like if the G acts in this way. And then sort of like now here there's a pi coming in. This is called a group representation. So like that the pi of the rotation matrix should act as the output of U. And sometimes we will choose the pi to be equal to the trivial representation, where that's basically, I mean that this one disappears. Sometimes we do, for instance, like if the output of U is a vector field itself, right? So you do want this vector field to be rotated. And so here is an image here taken from Weiler and Chaser here at the bottom. So for instance, now so like if we have an image and we rotate it, so like if the values of the image are scalars, right, then we like might not want to do anything with the values themselves. But if the values are vectors, so like then so like in order to rotate the vector field appropriately, we might want to have that we also like rotate the vectors as we rotate the vector, like the domain itself. Okay, so now we can prove like a more general version of the theorem that I've shown you earlier. Now like for like general groups and not just for rotations. So if G acts isometrically on X, meaning that like G acting on U, so like the norm of this is the same as the norm of U. Then if we have some functional J, which is invariant with respect to the group action, and if J is well defined and has a single value prox operator, just like for all of these conformities to make sense, then the prox is equivariant with respect to the group action, in the sense that sort of like the group acting on the group element acting on U, the prox of that is the same as the group element acting on the prox of U. The proof does indeed generalize to variational regularization. So like the counterexample that I had before with the in-painting. So like one can prove this for variational regularization if A itself is equivariant, like if it makes sense, and if it is indeed equivariant. And so kind of like if you have a kernel, right, then you can always with your group action shift something to the kernel, right? So like if you have a kernel, then A will like never be equivariant. Okay, so how does this now work together with neural networks? So how do we get equivariant neural networks? So like first of all, there is actually like a big calculus, sort of like with equivariant mappings. So if we have two mappings which are equivariant, then their composition is also equivariant. We have that if we have two mappings which are equivariant, then the sum is equivariant, and the identity function is also trivially equivariant. I will show you on the next slide that there are linear operators which are non-trivial and are G bar equivariant. Like this G bars is like this like roto-translational group that I've shown you on the previous slide. Then biases are equivariant as long as the bias itself is invariant. And there are nonlinearities which are G bar equivariant. Again, I will show you in 2 slides. And so therefore, so like with all of these building blocks, we can now construct neural networks in the usual way, right? So for instance, we can have one layer which is equivariant, and then like n layers, and then we like compose this together, and we again get something that is equivariant. Then our standard feed-forward neural network, we can choose like let's say like the nonlinearity and the A and the bias in the ways this one is equivariant. And the same with the ResNet, right? Since the identity is equivariant and the sum is equivariant. So it's like as long as we can construct such like a feed-forward type layer, then again we can construct bigger neural networks which are all equivariant. Okay, so now it gets a bit technical here. So like now in order to simplify things, this is now for the trivial representation. The formulas for arbitrary representations you can find in our paper. And so kind of like in a nutshell, sort of like the take-home message is that there are non-trivial linear operators which are G-bar equivariant, as long as, and these are the convolutions, as long as the kernel satisfies some additional constraint. So in practice, so sort of like in more detail, so like how this is, so like if we have an operator acting between two spaces, for instance, could be L2 or something else, and this phi is a linear operator defined in this way, then this is G-bar equivariant if and only if there is a small k, so like now, so there's a capital K, right? Has two inputs, x and y. This small k has only one input, right? So like, if there is a small k such that we can represent the linear operator as a convolution, and in addition, this k needs to be H invariant, right? And you remember like H is a subgroup where you can like think about as like rotations, for instance. So like for all elements R and H, we need to have that however, so like X being first like rotated as a special case, then sort of like this needs to be the same. So like for instance, like if if you think about a K, for instance, like if you have, let's say, like a Gaussian kernel, right? Then that would be indeed invariant with respect to rotations, right? And so like overall the convolution operator that comes from it then would be G-bar equivariant. Okay, so for non-linearities, like the story is similar. So like again, so like things are rather complicated for non-trivial representations. Again, please have a look in the paper if you're interested. For trivial representations, things are still a bit complicated, but much easier. And so like in a nutshell, there are non-linearities that we can pick. So like in more detail, so like in the literature, there are two non-linearities that you can choose. And so maybe like this one, let's not go into like too much detail, but maybe like let's talk about this point-wise, component-wise non-linearity. Since this is the one that we also usually choose in practice, right, where the non-linearity usually acts component-wise on vectors. That analog for continuous images then will be of this form, right? So it's a non-linearity acting on an image evaluated at some x, right? So this now, first of all, it acts point-wise, right? That's what this equality means. And now, so like if now this x is a vector here, then sort of like it's also like should act component-wise, in the sense that sort of like its ith component is nothing else than sort of like again some scalar function applied now to this scalar value xi. Okay, so like both of these non-linearities are G-bar equivariant. All right, let's talk about some numerical results. As I said before, so like we want to have, we're looking at into two application areas, CT and MR, and so like a little bit more detail on exactly what we have been looking at. So like we look at two open data sets. So like here, there's an open data set which is coming from low-dose CT, and so here's like this is now how our ground truth images look like. And so now then we simulate some data based on this, and if we now apply a filter back projection to it, then this is how it looks like. So this gives like some feeling of sort of like how much undersampling and noise we've added to it. And similarly for like MRI, we're talking about like undersampling. And again, if you look at the minimum norm solution, this is how it looks like. So like this gives you some indication of like how much undersampling noise there is in the data. And so like both of these data sets are, I would say, like medium size, right? I mean, they're like fairly small compared to things like ImageNet, but then they are like of like proper size, like a few thousand images. And so we use here like 5,000 images for training, 200 images for testing, and 1,000 images for validation, and the same for the fast MRI dataset. Okay, so here's some results. So basically, so like what we compare here are two different methods. So these like learned proximal gradient descent, and once the neural networks involved, they are convolutions. So here now we call them like ordinary convolutions. So they are translationally equivariant. And what we call here equivariant, these are where the convolutions are, where the neural networks are equivariant with respect to roto-translations. So these are the other two methods, and here on the right you can see the ground truth. And so like what do we see from these results? Like first of all, we see that sort of like SSIM is maybe like about the same, maybe slightly higher for the equivariant one. PSR is quite a lot improved. But maybe like more important than looking at these numbers is looking at the images directly. So like the results from the equivariant, the roto-translational equivariant neural network, So like they have like much better results. Like there's like a lot of like cloudiness going on here. This is like a very like nice result. And can you see this on there? Maybe not so much, but here, for instance, I mean, like another area that I could have highlighted. So there's some spurious artifacts here at the bottom that actually like look fairly realistic, like a bit of like dark areas that which you like can't see in the roto-translational equivariant neural network. Okay, some quantitative results. And so here the take-home messages I would say are a bit similar in the sense that sort of like the roto-translation one works like a bit better. And so like in more detail here on the x-axis with the training size. And so here on the left in total are the upright test images. So like the test images just taken as they are from our database. And here on the right are the results for if we take the test images and artificially rotate them, right? Looks like it's all about equivariance with respect to translations. And so what we can see here is sort of like the equivariant one here in blue, the ordinary one in orange. So if we have like a large amount of training data, then actually like it's like doesn't have like much of an effect, but like the difference is really significant once you go to like small training sizes. And now if we apply everything onto the rotated test images, there the difference is bigger, right? So even for like small training data sets, the ordinary one breaks more easily, but also kind of like the transitions of like when the equivariant one is favorable compared to the convolutional one, sort of like is already here at like 100, 200 training images. So here we can see like a difference on the rotated test set. The story for MR is quite similar. So like I don't show you any images here, but let's look at the quantitative results. So that like overall the roto-translation one seems to be better than the ordinary one if you like don't have that much training data. But here now the difference, on the one hand, the difference is smaller as we have already seen on CT. I don't know why that is. It's kind of an open question. But there's another thing that's very subtle that our reviewers recognize with paper that we haven't even seen ourselves. And can you see it from here? So maybe like if we focus, for instance, on training size 10, can you see that this bar is higher than this bar? Maybe I should have drawn a line. Can you see this? So this is kind of like a bit strange, right? So like, why would both methods work better on the rotated test images than on the upright test images, right? Because they are supposed, like at least in a continuous sense, they are supposed to, at least the equivariant one, kind of like they're supposed to work kind of similar or the same. So this is a bit sort of like surprising, and we have made some experiments to look into it, why it is. So we were speculating first that this is because when you rotate images, when you rotate discrete images, you need to interpolate them. So it also has a smoothing effect on the images. So we were like numerically testing this. So now here, so like on the in the left graph, you can see the equivariant one, on the right the ordinary one, and now the blue one are the unaltered images, and the orange one is rotated. But what I mean with rotated is that we rotate it by a certain number of degrees and then rotate it back, right? Which is just like we have done twice in like some interpolation, and we've basically done exactly like the same kind of smoothing that you would do by rotations, but there are no rotations in the end. And what you can see here with the results, that sort of like the blue one seems to lie significantly underneath the orange one, meaning that the smoothing coming from rotating back and forth actually, so like both methods improve when you smooth the images this way, which is kind of like it's an interesting observation. Okay. So with this, I would like to conclude the talk. So first of all, I think one of the main take-home messages is that there is no need for data augmentation, right? So we can have like mathematically guaranteed equivariant neural networks by building them carefully. Then what we've seen is that solution operators for image problems, they generally may not be equivariant, because like it may not even make sense to talk about equivariance, but the proximal operators, they are usually equivariant. One thing that I didn't talk about before, but I would like to highlight it nevertheless. So like that this equivariant framework that I presented is computationally very efficient. So like at runtime, these are nothing else than convolutional neural networks. It's exactly the same. It's just like that we have chosen filters more carefully. So like during training time, we have needed to spend like a bit more extra effort, but at runtime, it's exactly the same. And then sort of like this can be useful for like many applications we've seen like CT and MR. And so like I would say like two take-homes is there. I think if you have a lot of training data, we don't see much improvement there. But like if you have like only like a few data points and you are interested in robustness, then this can be for you. And then so like in the future, there's like basically with like any research project, right? Like once you get started, so like the more you work on it, the more open directions there are. So like first of all, so we're interested in like in other groups. So we now focus on roto-translations, but there are clearly other groups of interest. So for instance, like scaling of intensities. So like what happens, let's say for instance, if you change the units of an image, right? Then let's say like if you go from, I don't know, meter to millimeter, right? Like it's like nothing else than like a global upscaling. So if you want to be equivariant with respect to units, this would form like a group. Then you can have like a scaling of the domain or some affine transformations of the domain. Then other image problems are clearly of interest. So I highlighted compressed sensing and trivial kernel because they're sort of like maybe kind of like this solution mapping composed with a for operator, maybe equivariant. And then obviously sort of like higher dimensions are of interest, like make it computationally feasible for like 3D imaging. But also sort of like maybe like there are some groups which are sort of like particularly suited to like dynamic image problems and so on. And again, so like if you want to see like more details, this is our paper. Thank you very much for listening.
Thank you, Matthias, for this awesome talk. Again, you can either write questions in the chat. I'll be looking at it, or just unmute and ask. There is one question from the audience. Martin?
Yeah, thank you. Thank you for the nice talk, cool stuff. I have probably two questions, if you allow me. So the first one was with your TV example.
Yeah.
So if I got it correctly, because obviously normally TV itself, or the ROF model is sort of rotation invariant, but because, so basically your A here is not equivariant, right? That's basically what causes the issue with, and you said something like that every kernel basically, or you have
every for operator that has a non-trivial kernel has this property. I mean, like it depends on the groups that you're talking about as well, right? But like if you think about like roto-translations or translations only, so like if you have a kernel that you can move into, right? I mean, so like now if you are in a more complicated scenario, let's say like undersampled CT, right? So what does it mean to move into the kernel, right? So like, not sure, maybe like there's some CT experts in the audience who can tell me what this means. But kind of like if you can transform your image or like some image that you can transform into the kernel, then there's no chance that you can be equivariant.
Yeah, I see. And my other question, could you think of, let's say, having data samples for which you think they are somewhat, they show some equivariance in them? Could you try to infer an equivariance rather than using equivariance to basically make reconstructions so better or rely on fewer data samples? Could you also try to infer?
So you mean to learn the group from data?
Yes.
We haven't thought about this. I think in some of the papers, I think they mentioned this, but like not that they have done it, but they mentioned that this would be of interest. Not sure what. So like my feeling is in computer vision literature, with like a super active topic in computer vision literature, my feeling is probably some people have looked into it, but I wouldn't know a paper.
Do you see any technical issues or anything that makes it sort of more complicated trying to infer? I mean, in terms of the optimization, the group, or do you think it could be relatively straightforward?
I mean, you would need to think about it. I mean, first of all, how would you learn this, right? So suppose you would need to parameterize the group, and you would want to do it in an unparametric way, I suppose, as possible, because you don't want to enforce a certain structure of the group. So from the top of my head, I have no idea, but I would be very interested in this, but I don't know. But it's a very, very interesting question, and the things of like, I think like roto-translation, I think are quite intuitive, but like, again, like if you are in a very complicated data set, maybe like we humans shouldn't tell the machines of like what are interesting equivariances, but rather learn from it. Yeah, sounds interesting, but I don't know. Yeah, thank you.
Okay, I think.
Yeah, thank you very much for the very interesting talk. I have a question concerning the equivariance. So I think it got already a bit obvious in your last example. I mean, the problem is if you have like your your group action on the image and you're in a discrete setting, then rotating and rotating back is not giving you the identity as it should be with this group formalism, because like if you take the inverse angle, it will be 0 in the identity transform. So does this mean that the network is designed in such a way that it's only equivariant in a continuous framework, or because like there's this discrepancy between working on discrete images and like that it doesn't really fit?
Yeah, so I think that is up to you, I would say. So there are groups for continuous images, but there are also groups for discrete images. So for instance, when you think about translations, right? So like if you were to translate a pixelated image by exactly 1 pixel, right? Then so like this is also kind of like a group, right? And you can like the inverse is you like move it back 1 pixel. So if you like to think discretely, so like there are groups of this form. So I personally like to think about these images as continuous images. So like therefore, like I'm more interested personally in continuous groups, and so therefore, sort of like basically here. So for instance, like with the roto-translation that we have done here, so like there, I mean also there, so you could have, for instance, like a subgroup of all rotations that moves by, let's say, like 90 degrees, right?
Mm-hmm.
And then we have no problems. It's like working on a pixel grid. But so like I personally sort of like I don't want to, let's say, like overtune towards pixelated grid, because maybe like in the end of the day we want to go beyond pixels, finite elements, whatever, right?
But like even if you do the rotations and your image is rectangular and you're rotating by 90 degrees, then the domain size will change.
Yeah,
which is
yeah, fair enough.
not too.
But then you can have like 180 degrees if you want to. But it's also like I don't want to advocate this type of thing, but you can do it, right? I mean, like, it does exist. So like I personally think that sort of like it makes more sense to think about it continuously. But then obviously sort of like then some of these equivariants that I talked about, right? When then discretize, you can't expect that sort of like the discretized system is 100% equivariant anymore. If you have discretized, it's a continuous world was equivariant, then obviously there is some error when you then do the discretization. But you can still hope, right, that if you make the discretization finer and finer, then you can like converge to the continuous setting.
Then maybe just one more question with respect to this. So you're always using images on Rn, right? So you're having somehow a domain which is itself invariant with respect to your roto-translational group. So you're not having like a domain with boundary or something which would be not itself invariant. So because like the difference is if you're just using a square and you're rotating it, then it won't match anymore. And if you're using Rn, I mean, you can shift it, you rotate it, it will be the same space. So it's
like, and with Rn, you mean like Rn by n?
Yeah, you're just using the whole space. So you're using the whole Euclidean space, nothing with a boundary.
Well, I mean,
what would happen is like if you have something with a boundary and you do a shift, like you eventually come out of the region and you somehow have to pad something where you don't know what the information is. And like if you just think of going once completely out and once completely back in, you will have just the padding information back in. If you have a domain without boundary, that cannot occur.
So we do have a boundary, right? So then we need to talk about boundary conditions, right?
Okay, yeah.
And so kind of here, so like I mean, in the numerical examples, I'll show you here in the end, right? Okay, so like here also, I mean, these are like cropped, right? So like there's like a lot of blackness around it, right? So like we use here like 0 boundary conditions. And so like since the image of interest, like since the region of interest going so far away from boundary, we haven't numerically observed any issues there. But obviously, sort of like here now, this one sort of like it's not. I mean, so yes, you could kind of move out of the field of view, right? And then if you then were to move back, then you have lost all your information. But we haven't observed any numerical problems in this regard. But also, I believe because kind of like the boundary was quite far. Because I think like, I mean, these are the cropped images, right? So like I think the original images, I mean, they go maybe until here or something, right? So like, there's a lot of blackness around them if you don't crop them. Yeah.
So as I understand it, your proximal operator and your regularizer are equivariant, but your networks aren't, and you explained how that's not necessarily a meaningful thing. So what sort of, do you have any thoughts on what sort of theoretical results you could put on these networks to say what, because you're seeing they empirically perform better, but how would you couch that in a theoretical statement?
That's very, very difficult. Also mean like maybe like one thing that is quite important here that I think the main message of the talk is really about this equivariance, and then we use it in a learned, so like in an unrolled proximal gradient descent method as a prox operator, but then you can use this also in like many other ways, right? And as we have seen, for instance, I mean this morning, but maybe like personally in my view, maybe like more interesting, so like the talk we had on Monday about this deep equilibrium methods, right? Also there you have like the same structure. So I think if you want to say something theoretically, it's like, because I think that these unrolled algorithms, I think they are not very amendable to theory, right? So therefore I think so like, so if you have some theory, for instance, like about the deep equilibrium methods, where I think also like, I think the speaker on Monday, I think so like she like didn't have any results, but I think that maybe that is an area where you can have some results. And then I think once you have them, maybe then you can say more when you have equivariance.
You even with the TV, you're saying it's not equivariance. The system is not equivariant.
The variational regularizer.
It's not equivariant. If you're in all cases, if you don't have an inverse model. So when can you? I mean, I'm just trying to think how one would articulate the theoretically where the gains are coming from in putting an equivariance on a regularizer rather than something else.
Yes, it's difficult. So I mean like one thing that kind of like in the computer vision literature, sort of like what's usually being referred to as sort of like sample complexity. So like that potentially sort of like so I mean as you have more structure on the network, you have a better sample complexity that you need fewer. I mean we empirically observed this, right? But I also make this like not theoretical. So that might be an option, but also like then the relation to the inverse problem, as in only use it as a building block for the inversion methods, that's quite difficult, I think, to make that step forward. But if you have any ideas, please do let me know.
Okay. Very quickly, because we should start in a minute.
Yeah, I was just wondering, how do you, in training, how do you enforce that your kernel has the, you show the theorem that says there exists one, but how do you actually do this for a discrete kernel?
So there are various options in the literature, and so what we follow is sort of like oops, let me go back. What we follow is is a software framework proposed by Weiler and Chaser, and so like that they call this steerable convolutional kernels. So like you have like some sort of like parameterizations of the kernel, and then so like for all of these parameters you have a certain equivariance, and then you can learn these ones. So like I would like refer. I mean, so like you can also check out our paper or the original source would be like Weiler and Chaser if you want to learn more about this.
Okay, thank you.
Thank you. Oh, we have something in the chat. Okay, I think Ozan is posted a couple of papers, links on archive for everyone to check out on this. Okay, then. So I think that since we have only 3 more minutes to the next speaker, we thank Matthias again. Thank you very much. Okay, so Thomas, are you there? And
yes, I'm here. Can you hear me? Hello. Hello.
If you are talking, we can't hear you.
I could hear you, Thomas. Okay. So it seems it's not on my